Good day, everyone. Today, I'll be presenting our laboratory activity 3, which is all about digital signal time transformation. The objectives of this laboratory activity are to understand the concept of time transformation, specifically time shifting, time scaling, and time reversal in digital signals. We also aim to apply Python programming to visualize these transformations and analyze how they affect discrete time signals. In the background, we learned that digital signals are commonly used in communication, control, and monitoring systems. In digital signal processing, or DSP, one of the key operations we often perform is time transformation. This includes three main types: time shifting, which moves the signal forward or backward in time; time scaling, which compresses or expands the signal in time; time reversal, which flips the signal around the vertical axis. These concepts are essential because they are widely used in telecommunications, radar systems, biomedical signal analysis, and even in disaster warning systems, where time manipulation of signals is necessary for analysis or synchronization. For the materials, we only need a computer with Python installed and the NumPy and Matplotlib libraries, which can be installed using pip install numpy matplotlib. Now, moving on to the procedure. We start by importing the necessary libraries. Next, we define a simple discrete time signal. We then plotted the original signal using plt.stem to clearly show its discrete nature. For time shifting, we created two variations of the signal: a right shift by 2 units, which delays the signal represented as x of n minus 2; a left shift by 2 units, which advances the signal represented as x of n plus 2. When plotted, we can observe that shifting only moves the signal horizontally. It does not change the amplitude or shape of the signal. The next transformation is time reversal. Here we reverse the signal by replacing n with negative n, effectively flipping it around the vertical axis. This means that the last value of the original signal becomes the first value of the reverse one. The plot shows how the signal reflects across the n minus n is equal to 0 axis, changing its symmetry. Finally, we explored time scaling, which involves expanding or compressing the signal in time. We did this by creating an expanded version using n expand is equal to 2 times n, which spaces out the samples and stretches the signal. The compressed version using n compress is equal to n divided by 2, which brings the samples closer together and makes the signal appear more compact. These operations visually demonstrate how scaling modifies the signal's density along the time axis. In the expected output, we observe 5 plots: the original signal, the time-shifted signals, both delayed and advanced, the time-reversed signal, and the time-scaled signals, expanded and compressed. Now let's go over the guide questions. First, what is the effect of time shifting on the position of a signal? Time shifting moves the signal left or right along the time axis, causing it to appear earlier or later in time. However, it does not affect the signal shape or amplitude. Second, how does time reversal change the symmetry of a signal? Time reversal flips the signal about the vertical axis at n is equal to 0, reversing the order of its values. As a result, the sequence is mirrored, changing the signal symmetry. And lastly, in what real-world applications can time scaling be applied? Time scaling is used in several real-world applications, such as audio playback speed adjustment, video slow motion or fast forward, telecommunications, and radar signal analysis. It's especially useful for modifying how fast or slow signals are processed or transmitted. To conclude, this laboratory activity helped us gain a deeper understanding of how time transformation affects discrete time signals. Through Python visualization, we were able to clearly see how shifting, scaling, and reversal change the position, orientation, and spacing of signal samples, concepts that are fundamental in digital signal processing. Thank you.